Openstax Contemporary Mathematics, Chapter 2, Section 3, Constructing Truth Tables. Figure 2.8. Just like solving a puzzle, a computer programmer must consider all potential solutions in order to account for each possible outcome. Credit. And it looks like a picture of people trying to solve a very large puzzle. Learning objectives. After completing this section, you should be able to 1. Interpret and apply negations, conjunctions, and disjunctions. 2. Construct a truth table using negations, conjunctions, and disjunctions. 3. Construct a truth table for a compound statement and interpret its validity. Are you familiar with the Choose Your Own Adventure book series written by Edward Packard? These game books allow the reader to become one of the characters and make decisions that affect what happens next, resulting in different sequences of events in the story and endings based on the choices made. Writing a computer program is a little like what it must be like to write one of these books. The programmer must consider all the possible inputs that a user can put into the program and decide what will happen in each case. Then write their program to account for each of these possible outcomes. A truth table is a graphical tool used to analyze all the possible truth values of the component logical statements to determine the validity of a statement or argument along with all its possible outcomes. The rows of the table correspond to each possible outcome for the given logical statement identified at the top of each column. A single logical statement, P, has two possible truth values, true or false. In truth tables, a capital T will represent true values and a capital F will represent false values. In this section, you will use the knowledge built in statements and quantifiers and compound statements to analyze arguments and determine their truth value and validity. A logical argument is valid if its conclusion follows from its premises, regardless of whether those premises are true or false. You will then explore the truth tables for negation, conjunction, and disjunction, and use these truth tables to analyze compound logical statements containing these connectives. Man, I'm thirsty. Interpret and apply negations, conjunctions, and disjunctions. The negation of a statement will have the opposite truth value of the original statement. When P is true, not P is false. And when P is false, not P is true. Example 2.12. Finding the truth value of a negation. For each logical statement, determine the truth value of its negation. 1. P. 3 plus 5 equals 8. 2. Q. All horses are Mustangs. 3. Not R. New Delhi is not the capital of India. Solution. 1. P is true because 3 plus 5 does equal 8. Therefore, the negation of P is not P. 3 plus 5 does not equal 8 is false. 2. Q is false because there are other types of horses besides Mustangs, such as Clydesdales and Arabians. Therefore, the negation of Q, not Q, is true. 3. Not R is false because New Delhi is the capital of India. Therefore, the negation of not R, R is true. Your turn 2.12. For each logical statement, determine the truth value of its negation. 1. Not P. 3 times 5 equals 14. 2. Not Q. Some houses are built with bricks. 3. R. Abuja is the capital of Nigeria. A conjunction is a logical and statement. For a conjunction to be true, both statements that make up the conjunction must be true. If at least one of the statements is false, the and statement is false. Example 2.13. Finding the truth value of a conjunction. Given P, 4 plus 7 equals 11, Q, 11 minus 3 equals 7, and R, 7 times 11 equals 77, determine the truth value of each conjunction. 1. P and Q. 2, not Q and R. 3, not P conjunction Q. Solution. P is true and Q is false. 1. P is true and Q is false. Because one statement is true and the other statement is false, this makes the complete conjunction false. 2. Q is false, so not Q is true, and R is true. Therefore, both statements are true, making the complete conjunction true. 3. Not P is false, and Q is false. Because both statements are false, the complete conjunction is false. Your turn 2.13. Given P, yellow is a primary color, Q, blue is a primary color, and R, green is a primary color, determine the truth value of each conjunction. 1. P conjunction Q. 2. Q conjunction R. 3. Not R conjunction P. Caution. The only time a conjunction is true is if both statements that make up the conjunction are true. A disjunction is a logical inclusive OR statement, which means that a disjunction is true if one or both statements that form it are true. The only way a logical inclusive OR statement is false is if both statements that form the disjunction are false. Example 2.14. Finding the truth value of a disjunction. Given P, 4 plus 7 equals 11, Q, 11 minus 3 equals 7, and R, 7 times 11 equals 77, determine the truth value of each disjunction. 1. P or Q. 2. Not Q or R. 3. Not P, disjunction Q. Give me one sec. Solution. 1. P is true and Q is false. One statement is true and one statement is false, which makes the complete disjunction true. 2. Q is false, so not Q is true, and R is true. Therefore, one statement is true and the other statement is true, which makes the complete disjunction true. 3. Not P is false and Q is false. When all the component statements are false, the disjunction is false. Your turn 2.14. Given P, yellow is a primary color, Q, blue is a primary color, and R, green is a primary color, determine the truth value of each disjunction. 1. P disjunction Q. 2. Not P, disjunction R. 3. Q disjunction R. In the next example, you will apply the dominance of connectives to find the truth values of compound statements containing negations, conjunctions, and disjunctions, and use a table to record the results. When constructing a truth table to analyze an argument where you can determine the truth value of each component statement, the strategy is to create a table with 2 rows. The first row contains the symbols representing the components that make up the compound statement. The second row contains the truth values of each component below its symbol. Include as many columns as necessary to represent the value of each compound statement. The last column includes the complete compound statement with its truth value below it. Then it looks like there's 2 videos. Logic part 2, truth values of conjunction. Is an and statement true or false? In logic part 3, truth values of disjunctions. Is an or statement true or false? Example 2.15. Finding the truth value of compound statements. Given Q, 4 plus 7 equals 11, Q, 11 minus 3 equals 7, R, 7 times 11 equals 77. Construct the truth table to determine the truth value of each compound statement. 1. Negation P, negation Q, or R, negation P, or Q, and R, not, parentheses, P and R, close, or Q. Solution. 1. Step 1. The statement, not P and Q or R, contains 3 basic logical statements, P, Q, and R, and 3 connectives. Tilde, up and down. When we place parentheses in the statement to indicate the dominance of connectives, the statement becomes parentheses, 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 not close, down caret, Q, close, up caret, R, close. Step 2. The table needs columns for P, Q, R, not P or Q, and not P or Q and R. Step 3. The truth values of P, Q, R, and not P are the same as in question 1. Step 4. Next, not P or Q is false, or false, which is false. So we place an F below the statement in the table. This is the only time that a disjunction is false. Step 5. Finally, not P or Q and R are the conjunction of the statements not P or Q and R. So the expressions evaluate to false and true, which is false. Recall that the only time an AND statement is true is when both statements that form it are also true. The complete statement, not P or Q and R, is false. And here's a little table below. P is true, Q is false, R is true, not P is false, not P or Q is false, and then not P or Q and R is false. 3. Step 1. Applying the dominance of connectives to the original statement, we have parentheses, parentheses, not, parentheses, P and R, close, close, or Q, close. Step 2. So the table needs the following columns. P, Q, R, P and R, not P and R, and not P and R or Q. Step 3. The truth values of P, Q, and R are the same as in questions 1 and 2. Step 4. From the table, it can be seen that P and R is true and true, which is true. So the negation of P and R is false, because the negation of a statement always has the opposite truth value of the original statement. Step 5. Finally, not P and R or Q is the disjunction of not P and R with Q. And so we have false or false, which makes the complete statement false. And then here's a little table. P, Q, R, P and R, not P and R, not P and R or Q. So P is true, Q false, R true, P and R true, not P and R, false, not P and R or Q, false. Your turn 2.15. Given P yellow is a primary color, Q blue is a primary color, and R green is a primary color, determine the truth value of each compound statement by constructing a truth table. 1. Not Q and P or R. 2. P or Q and not R. 3. Not parentheses P and R, close, and Q. Construct truth tables to analyze all possible outcomes. Recall from statements and questions that the negation of a statement will always have the opposite truth value of the original statement. If a statement P is false, then its negation not P is true. And if a statement P is true, then its negation not P is false. To create a truth table for the negation of statement P, add a column with the heading of not P, and for each row input the truth value with the opposite value of the value listed and the column for P, as depicted in the table below. So here we have negation, so we have column P, we have true and false for the possibilities, and then so not P would be false and true. Conjunctions and disjunctions are compound statements formed when two logical statements combine with the connectives and or respectively. How does that change the number of possible outcomes and thus determine the number of rows in our truth table? The multiplication table, also known as the fundamental counting principle, states that the number of ways you can select an item from a group of n items and another item from a group with m items is equal to the product of m and n. Because each proposition P and Q has two possible outcomes, true or false, the multiplication principle states that there will be 2 times 2 equals 4 possible outcomes, which is the set true, 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 false, false, true, false, false. The tree diagram and table in figure 2.9 demonstrates the possible outcomes for two propositions. True for when P is true, and then Q can be true or false when P is false. We have two statements, we have P and Q. P is true, true, false, false. Q is true, false, true, false. A conjunction is a logical and statement. For a conjunction to be true, both the statements that make up the conjunction must be true. If at least one of the statements is false, the and statement is false. A disjunction is a logical inclusive or statement, which means that a disjunction is true if one or both statements that make it are true. The only way a logical inclusive or statement is false is if both statements that make up the disjunction are false. So here's a little table: conjunction and disjunction or. So we have P, true, true, false, false. Column Q, true, false, true, false. So then P and Q, if P is true and Q is true, P and Q is true. If P is true, Q is false, P and Q is false. If P is false, Q is true, P and Q is false. And if P is false and Q is false, P and Q is false. And then the same thing goes for disjunction. If P and Q are true, then P is true and Q is true, then P or Q is true. If P is true, Q is false. P is false, Q is true, P or Q is true, and if P is false, Q is false, P or Q is false. Videos. We have logic part 4, truth values of compound statements with and, or, and not. Logic part 5, what are truth tables? How do you set them up? Example 2.16, constructing truth tables to analyze compound statements. Construct a truth table to analyze all possible outcomes for each of the following arguments. 1. P, disjunction, tilde Q. 2. Tilde, parentheses, P, up, Q, close. 3. Parentheses, P or not Q, close, and are. Solution. 1. Step 1. Because there are two basic statements, P and Q, and each of these has two possible outcomes, we will have 2 times 2 equals 4 rows in our table to represent all possible outcomes. True, 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 false, false, true, and false, false. The columns will include P, Q, not Q, and P or not Q. Step 2. Every value in column not Q will have the opposite truth value of the corresponding value in column Q. False, true, false, true. Step 3. Complete the last column, evaluate each element in column P with the corresponding element in column not Q using the connective or. The table goes as follows. P, true, true, false, false. Q, true, false, false. Not Q, false, true, P or not Q, true, true, false, true. 2. Step 1. The columns will include P, Q, P and Q, and tilde, parentheses, P and Q, close. Because there are two basic statements, P and Q, a table will have 4 rows to account for all possible outcomes. Step 2. The P and Q column will be completed by evaluating the corresponding elements in columns P and Q respectively with the AND connective. Step 3. The final column, tilde, parentheses, P and Q, close, will be the negation of the P and Q column. So we have column 1, P, next true, true, false, false, Q, true, false, P and Q, true, false, false, not P and Q, false, true, true. Step 3. Step 1. This statement has 3 basic statements, P, Q, and R. Because each basic statement has 2 possible truth values, true or false, the multiplication principle indicates that there are 2 times 2 times 2 equals 8 possible outcomes. So 8 rows of outcomes are needed in the truth table to account for each possibility. Half of the 8 possibilities must be true for the first statement, and half must be false. Step 2. So the first column for statement P will have 4 T's followed by 4 F's. In the second column for statement Q, when P is true, half the outcomes for Q must be true, and the other half must be false. And the same pattern will repeat for when P is false. So column Q will have true, true, false, 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 false. Step 3. The column for the third statement, R, must alternate between T and F. Once the 3 basic propositions are listed, you will need a column for not Q, P or not Q, and parentheses, P or not Q, close, and R. Step 4. The column for the negation of Q, not Q, will have the opposite truth value for each value in column Q. Step 5. Next, fill in the truth values for the column containing the statement P or not Q. The or statement is true if at least one of the P or not Q is true, otherwise it is false. Step 6. Finally, fill the column containing the conjunction, parentheses, P or not Q, close, and R. To evaluate the statement, combine column P or not Q and column R with the AND connective. Recall that only time AND is true is when both values are true. Otherwise, the statement is false. The complete truth table is, so we have P, true, 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 false, 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 false. Q, true, true, false, false, true, true, false, false. R, true, false, true, false, true, false, true, false. Not Q, false, false, true, true, false, false, true, true. P or not Q, true, 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 false, false, true, true, and then finally P or not Q and R. True, false, 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 true, false. Your turn 2.16. Construct a truth table to analyze all possible outcomes for each of the following arguments. 1. P and not Q. 2. Not P or Q. 3. P and not Q or R. Video, Logic Part 6. More on truth tables and setting up rows and column headings. Determine the validity of a truth table for a compound statement. A logical statement is valid if it is always true regardless of the truth values of its component parts. To test the validity of a compound statement, construct a truth table to analyze all possible outcomes. If the last column, representing the complete statement, contains only truth values, the statement is valid. Example 2.17. Determining the validity of compound statements. Construct a truth table to determine the validity of each of the following statements. 1. Not P and Q. 2. Not P and not P. Solution. 1. Step 1. Because there are two statements, P and Q, and each of these has two possible outcomes, there will be 2 times 2 equals 4 rows in our table to represent all possible outcomes. True, 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 false, false, true, and false, false. Step 2. The columns will include P, Q, and not P and Q. Every value in the column not P will have the opposite truth value of the corresponding value in column P. Step 3. To complete the last column, evaluate each element in column not P with the corresponding element in column Q using the connective AND. The last column contains at least one false, therefore the statement not P and Q is not valid. So we have P, true, true, false, false, Q, true, false, not P, false, false, true, true, not P and Q, false, false, true, false. And yeah, so because only one of the possibilities was true. 17. Construct a truth table to determine the validity of each of the following statements. 1. P or not P. 2. Not P or not Q.